In Chapter 3, Section 1, we talked about the first derivative, how to use it to determine things like intervals of increasing, decreasing, first derivative tests, and all sorts of stuff like that. In this video, we'll talk more about the second derivative and how to use those properties to determine traits about the function, such as concavity and the second derivative test. But let's just do a quick recap of all of the main ideas from the first section of Chapter 3, because they will be important throughout the rest of this chapter as well. So recall that we define a function to be decreasing or increasing when the first derivative is either negative or positive, because increasing and decreasing describes the rate of change over time, and the derivative also does that. When the derivative is negative, it means the rate of change is getting smaller, or the function is decreasing over time, and exactly the same for when the function's first derivative is increasing or when it's positive. There's that correlation as well. And in between increasing and decreasing, sort of, using the first derivative test as a way of figuring out, well, if we have a critical value on a particular interval, if on the left-hand side the first derivative is increasing and the right-hand side is decreasing, that means it's going up and turning down, indicating that that critical value is most likely a maximum. But basically, critical values are points where the first derivative is either 0, a horizontal tangent line, or undefined. So there's two cases to remember about critical values, which could, basically indicate possible locations for mins and maxes. And that's sometimes. Because as we saw, sometimes you can have a critical value that is neither a min or a max. And there are certain cases when it's not, they don't always happen there, but if there is a min or max, it will have to happen at a critical value. So a new term, or a term that a lot of people are not familiar with, is what's called concavity. The concavity of a curve describes its shape. One of the ways you can think about it is like in the terms of a parabola. A parabola we have as being either upwards facing, looking kind of like that, or downward facing, looking kind of like that. You can kind of keep that idea to remember. What does concave up and concave down look like? It has to do with the curvature of the curve. Kind of, is the U shape shaping upwards, or is the U shaping downwards? And now it doesn't have to look exactly like a U in order to be concave, but that's the general visual look of what we call concave up and concave down. And really, it's very synonymous to the way we define increasing and decreasing with the first derivative. A function is decreasing when the first derivative is negative. A function is decreasing or is increasing when the first derivative is positive. The same exact thing is true for concave up or concave down. And we haven't really talked too much about second order derivatives in our class yet, but we will start confronting that a bit more now. But basically, what we refer to as f double prime of x refers to a second order derivative. So let's do a quick example of what a second derivative is. Like, let's just say we were to take an example like f of x is equal to x cubed. Sorry, you can't see what I'm writing. The first derivative would be, well, we could use the power rule here, which would be 3x squared. So what we call f double prime, or the second order derivative of f of x, would just be taking another derivative. Basically, we're treating this as our function and asking ourselves, what is the derivative of this on its second order? So, well, the derivative of x squared is 2x. 2x times 3 is 6x. And so, a function, we could differentiate it once, twice, and we could continue to differentiate it. What we call f triple prime would be the third order derivative, which in this case would be 6. And with a polynomial, eventually, if you keep differentiating it, it'll eventually turn into 0, just because if you keep running through that power rule, eventually you're going to get it down to a constant. And sometimes we even use a shorthand exponent. Technically, it's not an exponent, but just to, instead of writing, well, quadruple prime, quintuple prime, or whatever, that sort of notation is used for iterative derivatives. But we'll focus on we don't use derivatives past the second order too frequently in calculus. And also with Leibniz notation, we use the term d dx as the differential operator. So if we had d dx of a function y, we sometimes also write that as dy dx. So I thought I'd mention how do we write this in terms of derivative? But basically, if you took the differential operator, we often write as d dx squared. So like d squared dx squared, or you can kind of imagine that as d dx. I'm doing that twice. Again, it's shorthand notation. It's not an algebraic statement. Or, you know, we could also think about it like this: d dx of y. Or you could kind of think about that as d dx of dy dx. And basically how we often write this in using the square notation, as I was saying before, is d squared y dx squared. Because it is the derivative that's second order, not the y. And we put the square over here, which is a little bit strange to see in some cases. But basically, this is how you'd see a second order derivative in Leibniz notation. And it's important to note that it's not the same thing as dy dx squared. These are not equivalent. This would mean the first derivative, quantity squared, is actually an algebraic statement where you're multiplying it to itself. Whereas this means the second order derivative, just like here. And again, we would kind of differentiate that between, well, if we took f of x squared, that's not the same as f double prime. Those are different meanings, just like these have different meanings. So we'll go ahead and erase all that. And similarly for third, fourth order derivatives, you just change the exponent on the ddx. So let's go back to concavity now that I've talked about the notation of second order derivatives. But basically, if the second order derivative is increasing or positive, then we would refer to this as being called concave up. Kind of like I was saying before, if we're looking at this example graph, the first graph here, it seems to be facing upwards in terms of its curvature, and that's exactly what concave up means. Sort of looks like an upward parabola, or a little chunk of it at the very least. But if we look at it, it's there's a couple ways in which concave up is defined as it's described in the graph. Either as the first derivative is increasing, but if something's increasing, that means that its derivative is positive. So a synonymous statement to having your first derivative increasing is to have your second order derivative being positive. And this is the way that I would recommend thinking about what is concave up. How is that defined mathematically? But basically, the second order derivative is positive. Just like with increasing, the first order derivative is positive. But if we think about what does f prime increasing mean, basically that means the slope of the tangent lines are getting larger, because that's what the first derivative does, tells us the slope of every tangent. And if you look at the graph, notice that if we start on the very left-hand side and look at the tangent line over here, for example, it seems to be fairly steep and negative. So let's just say -3 or -4. And then as I move along the curve, it's getting a little bit less steep. So maybe that's -2. And then we move over here, maybe the slope is -1/2. But notice that the slope is actually getting larger. Technically, it's getting less steep, but it's because it's getting less negative. And then as, you know, if we keep going along the curve, let me erase that. There's a point at which it has a minimum value on that, which usually indicates concave up, but not always. And again, so it's kind of like getting negative, 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 but it's getting gradually larger and larger and larger, eventually trending towards 0. And then as we continue going to the right, notice now it's like approximately maybe +1/2. Or again, we don't have any labels on our axis, so we don't really know, but it's getting, if you can see what I'm saying, the slope is going from sharply negative, gradualizing out to more positive. That sort of change is what's indicative of concave up. Again, always done from left to right. Now concave down, exactly the opposite idea. If your first derivative is decreasing, that means the slope of the tangent line is going from positive to negative. Actually, sorry, it looks backwards in the camera, but you know, say we have positive slope here. You know, like looking at the left-hand side, positive. As I move to the right, it's getting less and less. It's then going to 0, then going to -1, -2, -3, and so forth. The slope is getting less and less and less, more and more negative as we go from left to right. And again, that would be you know, since those slopes are getting smaller, that would be the same as g prime being decreasing. And again, in order to have a function be decreasing, that's always defined to be when its derivative is negative. So that's why the second derivative needs to be negative for a function to be concave down. And really what I recommend remembering from this is, what does concave up and down kind of look like, and then how do we define it mathematically? Because again, just like we did last week, we can use the second derivative to determine intervals of concavity. And that's exactly what the test for concavity says. If f double prime is 0 on an interval, then the graph is concave up. If f double prime is negative, it is concave down. So let's do a quick example. Let's say f of x is negative 1/3 x cubed plus 6x squared minus 11x minus 50. It says find f prime and find f double prime. So you'd always want to do this first if you're trying to find concavity intervals. Or again, you could be able to look at a calculator and figure it out, but it's a little bit harder to tell exactly where it's concave up and concave down if you're not really used to the sort of idea of slope getting larger and larger and smaller. But basically, let's go ahead and do it. The first derivative, well, it's a polynomial, so we can go term by term. Drop the 3 would give us negative x squared, because 1/3 times 3 would go away and drop the power. Then we drop the 2, subtract 1, that would be plus 12x. And then derivative of x is 1, so negative 11 times 1 is negative 11, and derivative of a constant is 0. So our first derivative goes from degree 3 down to degree 2. And our second derivative should always lower by degree once again. So derivative of negative x squared would be negative 2x, and derivative of 12x would just be 12. And the derivative of 11 would be 0. And it says use your calculator to sketch each of these in the particular window. Let's go ahead and skip that for the immediate time. But look at something like over what intervals is f concave up? So getting back to that, if we take the second derivative, f double prime, it would have to do with when this is positive and when this is negative. Actually, let's go ahead and look at a graph of the function real quick, because it will help us see the connection between the calculus and the first and second derivatives. But let's not actually sketch all of them. Let's just take a peek at the first derivative, or the original function. And if I had to redo the packet right now, I might actually just provide the sketches so that we don't have to take the time to do this. But you know, they say hindsight is 50-50. And the graph of our function looks something like this. Oh, it actually is giving us a window to look at it in, so let me go ahead and use that. Negative 10 to 20 by negative 100 to 150. And that gives us a pretty good idea of what our function looks like. Okay, let's just create a sketch real quick. Something like that. This is from negative 10 to 20. And negative 100 to 150. Okay. And so kind of getting back to the idea of concavity here, notice that part of the curve appears to be concave up, sort of looks like an, you know, the upward U. And then over here, it sort of looks like an upside down U. And, you know, it's totally different from intervals of increasing and decreasing. And another question is, where does it switch from concavity? Where does it switch from one to the other? But that's exactly what finding the second derivative can help us do. And this is a sketch of f, and we're just going to cross those out because don't necessarily need to go through all this. But basically, if we take the second derivative and figure out where it's positive or negative, so f prime of x is negative 2x plus 12. And if we figure out where the critical value is for the second derivative, the 0 value always helps us to determine where it switches between positive and negative. So if we set this to 0 and solve, again, this is kind of an idea that we use with the second derivative test. So we're going to discuss the sense of why this works. Basically, we can solve where it's equal to 0, 6. And that is like the point where it's switching concavity. Kind of like with increasing and decreasing, the critical values swap where it's changing between increasing and decreasing. The value where the second derivative is equal to 0. This is not called a critical value, by the way. This is called an inflection point. We'll define this soon. But basically, it's going to be concave up until 6. And that would be consistent with when the second derivative is positive. And if we look at the second derivative, like, you can always just plug numbers into this. But let's say we plug in a negative number into this. This is always going to be positive when any negative is plugged in. So basically, f double prime is positive on the intervals from negative infinity up until 6. And then once it hits 6, then it becomes 0. Then let's say we plug in 7, 8, or 9 into this, anything larger than 6, or even 6.1, this would now become negative, because the negative 2 times 7 would be negative 14, and this term would outweigh this term in terms of positivity and negativity. But this is consistent with when the original function is concave up and concave down by definition, because when f double prime is positive, that indicates concave up. So same interval, and that's kind of the point of looking at all of these things. The original function concave up when the second derivative is negative or positive. And also you can, if you were to look at the first derivative and take a peek at the graph, it would actually be a parabola. Let's go ahead and do that real quick. Negative x squared plus 12x minus 11. And take a peek at that. Notice that it's a parabola which has a vertex at what appears to be, well, actually we can't tell quite exactly where it's at, but it appears to be increasing up until a very particular point. Let's go ahead and zoom standard on this. But it seems to be increasing up until 0 and then decreasing. Something's wrong here because this should not be, oh, I typed it in incorrectly. So it should have matched up with these other answers is why I was trying to make a point about the connection between all of the different types of derivatives of a function and how they relate to one another. But I messed up what I typed in. So let me go ahead and go back to the window that I was using before and graph this parabola, which, there we go, that is looking correct. Notice that it is increasing up until a particular point, the maximum of the parabola. Again, this is a derivative of f prime. It's increasing from negative infinity up until 6, the vertex. Then once it hits the vertex, it starts decreasing from 6 to infinity. It goes downward. And there's a connection between all of these things. That is kind of the point of this example. In the next video, we'll talk more about concavity, the second derivative test, and again, using all these ideas to determine things.